All right, so I'm going to go over some simple circuits, looking at how to find the resistance through a circuit and how to solve for current, the equivalent resistance, current, and power. And so let's go ahead and start. So if I were to draw a circuit, I'm going to draw a series circuit. So I'm going to have a battery, so that way this is the positive end of the battery and this is the negative end of the battery. And the battery is going to be leading to a wire here, so that way the current flows in this direction. That is the conventional current. I'm going to put a resistor. It should look something like that, where it's going to have 3 peaks and 3 valleys, if you will. That's the proper way to draw it. Oops, excuse me. And so I've got one resistor there. I'll call that R1. Let's say that has a resistance of 2 ohms. And then I'm going to have R2. And that'll have a resistance of 3 ohms. And then I'll have R4. I don't know why I said R4. It should be R3. And that will be an equivalent resistance of just, let's say, 6 ohms, just to make something different. And then I'm going to complete the circuit. You'll have to excuse my drawing there. And so now I've completed the circuit. And what I want to do first is, if I have questions, let's say, for example, I want to find the power through the circuit. There's a sequence and order in which I need to do things. I need to first find the equivalent resistance. I need to then find the current. And then I can find the power through the circuit. Okay, so first, in order to find the equivalent resistance for a series circuit, the equivalent resistance across the entire circuit will be equal to R1 plus R2 plus R3. That is for a series circuit specifically, not parallel, but series. So we are simply going to add up those together. So that's 2, 3, and 6 is going to give us, what, that's 11. So that is going to give us an equivalent resistance of 11 ohms across the circuit. So the equivalent resistance is equal to 11 ohms for our series circuit. All right, so now that we've found the equivalent resistance across the circuit, we now want to find the current. Well, current is equal to V over R, so we need to know the voltage of the system. So let's make this a 12-volt battery. That's a pretty typical number to use. So a 12-volt battery, so that would give us a 12 volts over a resistance across the entire circuit of 11 ohms. So our current across the entire circuit, you'll have to excuse me, I'll have to actually calculate that on the fly. So it's going to be 12 divided by 11, giving us 1.09. Let me just round that off to 1.1. And that is going to be the unit of amps, so 1.1 amps. So the current is equal to 1.1 amps. All right, so now that we've got the current across the circuit, that is how much current is actually flowing through the entire circuit. Please be aware that any current that flows here through this wire must also flow through that particular resistor, resistor 1. It must also flow through resistor 2 and flow through resistor 3. Any current that goes through the first one must also go through the rest in series. That is true only in series. So they will all have the same current flowing through them. They all will have 1.1 amps of current. But what about the power? The power is equal to IV. So the current being the 1.1 amps roundabout, multiply that by the voltage, which is 12 volts. So across the entire circuit, we're going to have, excuse me for a second here while I actually run the number on that. About 13.1. So 13.1 watts is the unit. Watts the unit? Of course it is. So 13.1 watts is the power that goes through this series circuit. All right, so we've gone through, found the equivalent resistance, found the current, and found the power for each of these. If I wanted to continue, I can also ask another set of questions here. Namely, I can ask about each specific resistor. So firstly, I can ask about resistor 1. How much current is going through each resistor, or resistor 1, and what's the voltage drop across each resistor? Well, as I said before, the current is the same for all resistors. So the current for resistor 1 is equal to the 1.1 amps. The current for resistor 2 is equal to 1.1 amps, and the current for resistor 3 is equal to 1.1 amps. It's the same for all of them. However, the voltage for resistor 1 is equal to the current for resistor 1 times the resistance of resistor 1. And so this is the voltage drop. Okay, this is the, let me put in parentheses here, it's the voltage drop across resistor 1. So resistor 1 has 2 ohms of resistance, and it is in fact still the 1.1 amps of current. So 1.1 amps times the 2 ohms of resistance. Let me go ahead and run that number. So we've got 1.1 times 2, that's what, 2.2, right? I can't do the mental math apparently. 2.2, and that is going to be volts. That is going to be 2.2 volts of voltage dropped across resistor 1. For resistor number 2, the voltage drop will be the current through resistor number 2 times the resistance of resistor number 2. So again, we've got 1.1 amps times the resistance, that was 3, so 3 ohms. And so 1.1 times the 3 is giving us 3.3, and that's 3.3 volts of a voltage drop across resistor 3. Oh, excuse me, didn't mean to do that. Didn't mean to do that either. That's what I meant to do. Just wanted to move it over just a little bit. Okay, so that way I can do the voltage drop for resistor number 3 is equal to the current through number 3 times the resistance of number 3, and for that one it was a resistance of 6, so 1.1 amps times 6 ohms of resistance is going to give us 6.6, and that is volts. 6.6 of a voltage drop. I suppose I could have circled it since I did that to the rest. There we go. Okay, I feel better now. Okay, so we have a voltage drop of 2.2 and 3.3 and 6.6. And if you were to add those up, you would get 12.1. Of course, there's some rounding issues, so that should make sense, that you should get the total voltage across the entire system. Now, let's go back up. We have 12 volts. If I were to get a voltmeter, let me erase this stuff here. If I were to get a voltmeter, so here's my voltmeter with my dial, and I'm going to put the negative end here, and I'm going to put the positive end of the voltmeter here. And the reading that you would get on the dial, on the digital scale, or whatever it may be, is going to be 12 volts. But if I were to go to here, it would not read 12 volts. It will have dropped some value. It will have dropped a value of 2.2 volts. So 12 minus 2.2 would give me, what, 9.8. That would give me 9.8 volts. So that would be the voltage that I would get there. Let me get rid of the 2.2. So if I were to put in a lead here, the voltmeter would be reading 9.8 volts. So the voltage here is 12 volts. The voltage here at this point is 9.8 volts. Well, what about the voltage here? Well, it went from 9.8 and it dropped 3.3. So it drops 3.3 volts. So the 9.8 minus 3.3 would give me 6.5 volts. So 6.5 is what I would be reading here. And then, since this is my last my last resistor, I know that this is going to read 0 volts. It's going to read 0 volts there. And of course, it drops the 6.6 volts. Of course, there was a little bit of rounding going on there. So it drops approximately 6.5 or about 6.6 volts there to get me down to 0. And so each resistor gives me a voltage drop. The way to think of it is this. Okay, as an analogy, think of it this way. Think of the battery as a pump. Think of it as a pump. It's an electron pump. You can make the analogy to water. So if it was a pump pumping water, it would pump water up to some height, because remember that voltage is like the potential energy per charge. It is like having some sort of potential energy, some gravitational potential energy with water. So it's like a water pump, pumping water to some height. And then the resistor would be like a waterfall, where the voltage drop across the resistor would be similar to the height of the waterfall. Remember that there's a certain amount of current, right? There's current that is flowing through here. The current refers specifically to the number of electrons per second, or in this case, in the analogy, it could be the number of water molecules per second. And so it drops some height, and then in the next resistor, it drops yet another height. And then it drops yet again and gets down to its base level, and there's essentially a pool of water, and then the pump pumps the water back up. So that is a series circuit. Now we've got to go through the whole thing again with a parallel circuit. All right, so let's do that. In fact, let me just, there we go. Okay, so parallel. Let me do the same sort of thing with a parallel circuit. So I've got a battery, and I'm going to draw a parallel circuit. And there's more than one way to draw this parallel circuit. If I were to draw it pretty small, I'll do it small here, that way you guys can see it. I could also do it like this. It's the exact same thing. Right? So there's multiple ways to draw it, so I do in fact have a resistor there. As long as it has multiple paths for it to go through different paths for the electrons, it's parallel. So if you notice, it's the same for all three. So this is going to be my resistor 1, my resistor 2, my resistor 3. And if I again make a 12-volt battery, if I say that this is going to be 2 ohms again, I can make this 3 ohms again, and make this, what the heck, how about 6 ohms yet again. And so, again, I want to find all these same answers about this particular circuit. And so the equivalent resistance. So the equivalent resistance works very differently for a parallel circuit. For a parallel circuit, 1 divided by the resistance equivalent, or equivalent resistance, is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And so be very careful about your fractions and making sure that you take the reciprocals. All right, let me move this stuff down a little bit so we can have some room to work. All right, so that means that the 1 over the equivalent resistance is equal to 1 over 2 plus 1 over 3 plus 1 over 6. And I need to find a common denominator and the whole bit. So let's do that. All right, so common denominator will be 6. So 3 over 6 plus 2 over 6 plus 1 over 6. And don't forget that's equal to the 1 over the equivalent resistance. And so this is going to give me 6, 6, right? So this is equal to 1. So 1 ohm is the equivalent resistance. Well, isn't that convenient? I actually didn't mean to make it quite that nice, but it works. So that's actually not what I wanted to do for this one, to be honest, because I need to make it very clear, abundantly clear, that In fact, what if I were to change it? Yeah, let me go ahead and change it. So I'm going to make this a value of 12 ohms for that last one, so that way I can change these numbers. So sorry about that, but I've got to change it because I need to make a very strong point here. So I'm going to make this 12, and then go back through and find a new common denominator, which, what this would be 6/12. This one here would be 4/12. And of course, this is 1/12. And going through, I would find, 11/12. And so that would give me, again, that's 1 over the equivalent resistance. All right, let me just kind of go through, make sure that that seems right. So, yeah, okay. So we got 11/12 is equal to 1 over the equivalent resistance, but don't forget that this is equal to 1 over the equivalent resistance, which means that my equivalent resistance is equal to 12/11. Also, please, for any final answer that you're ever going to give me, please give it to me in terms of a decimal form, so that way it's always consistent for everybody. And so in this case, that would give us, who knows how I did it, but I got me an amperage of 1.1 amps yet again. Or I'm sorry, that's ohms. It's ohms. Don't yell at me too much. All right, so 1.1 ohms is our resistance across this circuit. It's our equivalent resistance. Don't forget to take the reciprocal of this at the end. All right, so what about the current? All right, so let me kind of go down a little bit and erase this stuff from before. So the current, I need to now find the current. So the current across the entire circuit is, again, equal to V over R. The voltage is 12 volts. The current is 1.1 amps. And I believe that gives us the 13.1, yet again, 13.1 amps. No, I have lost my mind. I need to stop making mistakes. That is, that's a smaller number. It's going to be making it because it's thinking of something else. Would be at 10.9. Let's do 10.9 amps. Sorry about that. So V over R, the voltage divided by the amperage for the entire circuit. Power is equal to IV. So the current of 10.9 amps times the voltage of 12 volts gives us 130.9 watts of power. 130.9 watts of power. And then lastly, we've still got these two questions about each individual resistor. So what is the voltage drop across each one, and what is the current that is flowing through each one? Because the current is going through, and then some of the current goes this way, some of the current goes this way, and some of the current goes this way. But the voltage across this entire area, across all those lines that I'm crossing, the voltage is the same. And then also the voltage is the same across these. So basically, the voltage is 0 volts here, and it is 12 volts here. And that is the same voltage drop across each and every resistor. So the voltage across resistor 1 is equal to 12 volts. The voltage drop across resistor 2 is equal to 12 volts. And the voltage drop across resistor 3 is 12 volts. But the current is different for each one. So the current across resistor, or going through resistor 1, is equal to V over R. So it's the 12 volts going across the resistor divided by the resistance of it, which is, I believe it was 2 ohms. So that would give us 6 amps of current going through that resistor. For the next one, the current going through resistor number 2 is equal to the voltage of resistor 2 divided by the resistance of resistor 2. That was what, 3? That was 3 ohms. So we are looking at the 12 volts divided by the 3 ohms. That gives us 4 amps. I don't know why I wrote the A twice. So 4 amps. And then lastly, for the current for the last one, we're looking at the voltage across resistor 3 divided by the resistance of resistor 3, which is 12 volts divided by the, I'm sorry, it was 12. I changed it to 12 ohms, and that gives us 1 amp. 1 amp going through the last resistor. All right. I know that that's a lot, but you know, hopefully that helps you on being able to solve these problems. Let me also go over some conceptual aspects of these resistors before I finish. When I had the series circuit, let me draw a small one here. When I had the series circuit, by having more resistors in series, it increased the resistance, because any current that flows through resistor 1, once it gets by the first one, it must then also have to go through the second. Imagine yourself trying to go through some sort of scenario like this, where there's something that's giving you resistance, you finally get through it, and then, oh gosh, there's another thing there giving you resistance, you have to go through it as well, and then yet again. So the more resistors you have, the more resistance it'll give you total, so it makes sense you have to add them up. However, in the case of the parallel circuit, since you have multiple paths that you can go, having more resistors in parallel decreases the resistance, it decreases it. So an analogy here could be like at the grocery store. So you're trying to check out of the grocery store. If they only have one lane open, then there's a lot of resistance in your way of being able to check out because there's people in the way and the whole bit. Versus if they open up 2 more lanes, that gives you 3 lanes to choose from. If you have some old lady here that's taking forever, actually no, that old lady would be here. She's taking forever. She's got a lot of resistance, so more people are going to wind up flowing through here, so there's going to be more current this way, and not quite as much, but a lot of current going through this way, and only a little bit of current going this way. And so the current is divided, but yet more resistors in parallel actually decreases the overall resistance because it gives more paths for you to be able to choose from and allows for more of the electrons to flow through per second, more charge to flow through per second. All right, so that is the last conceptual bit I wanted to talk about before I ended here. So hopefully it helps, and you guys have a good one. Thank you.